Welcome everyone to this week's CCNB seminar meeting. Welcome everyone online and welcome everyone here at Freie Universität. It's my great pleasure today to introduce Professor Bernhard Spitzer, or almost Professor Spitzer, who is expert in working memory research and was also for a while here at Freie Universität, and I have learned much from him. Collecting tons of data.
Not only
a great time. So Bernhard was originally starting his studies in Regensburg, was then coming later to join the group of Felix Blankenburg as a postdoc. This time, enormous productivity with PNAS, Journal of Neuroscience papers, one after the other. A lot about vibrotactile working memory. Then from there, Bernhard was going to Oxford to work together with Chris Summerfield for a while, and then coming back to Germany, having an own group at here the Max Planck Institute for Human Development, and now is in the moving to Dresden as almost professor. It's like gonna be soon, and it's a great pleasure. I'm very excited to hear the talk, something we are also interested in, had multiple speakers already here on working memory and on similar topics, so excited to hear talk.
Thank you very much, Timo. It's always a pleasure to come here in the neighborhood. And of course, I would have prepared lots of jokes on reimbursement of the travel costs for the 2-kilometer ride and so on, which I always do when I give a talk here. But I skipped this because I noticed I have lots of material and I don't want to overload the talk. Also, I apologize if there was some confusion potentially about the title. That is my fault. I did a late-minute change. So I'm going to talk coarsely about levels of abstraction of visuospatial information in working memory. If someone came for the long-term storage, which briefly was also in the title, please get in touch with me. I talk to you privately. I'll be happy to do that. So coming to this talk, I actually, and sorry, Timo, for showing the email, I received instructions. And the instructions were no less than sharing my vision about the future of working memory research. Thanks for this, team. I'm very humbled, of course, to be addressed with this question. I don't know if I do it justice. It also got me a bit intimidated, but I'm trying hard. So to get at least in some approximation there, I will at least pose bold questions. And as I said, I will focus only on one today. What is the nature of information in working memory? And that obviously is a huge question. And I very obviously won't provide a satisfactory answer in this talk, but I view it as a guiding question for some of the work in our lab. Also, I don't know whether I make it into the future, but to get as close as possible, I will present only very recent work. So work that has only very recently been published or is only in the process of being published. But maybe from the start. So working memory, maintenance and manipulation of information for an upcoming task. That's at least a very common definition you find in lots of textbooks and introductions to scientific papers. And it's a huge research field. So it's impossible, I think, to do it any justice in a brief compressed introduction. So I will only briefly highlight what I think are a couple of quite uncontroversial things about working memory. So one is that presumably such a function, maintenance manipulation of information for upcoming tasks, is presumably hugely important for almost every aspect of higher cognition, I would say, from decision-making, problem-solving, planning, language comprehension, production, etc., etc. So probably it's an important ingredient to the possibility even of higher intelligence. At the same time, and this is something I always find puzzling, it's also quite uncontroversial that working memory as we know it is presumably pretty small, or let's say very limited. So there is quite some controversy on how to precisely qualify or quantify this capacity limit, but I think most people would agree there's a clear limit. It's a limited resource. And this kind of tension is something that fascinates me. So how is it, and many others, I guess. So how is it possible that we can be so kind of intelligent? How is human intelligence possible when it runs on such a tiny or lousy, you could say, memory store as a working memory? Or the other way around, what is so amazing about working memory that it suffices for all these feats of the mind, despite being so small and limited? Well, and one potential angle to look at this could be that potentially it's not even so very important how small or how limited working memory is in terms of the information it can retain. But perhaps the true strength of working memory is that it's so flexible and that it can adaptively always provide kind of the right information at the right time, and apparently in a way or format that suits our momentary goals and cognitive tasks. Just as a quick illustration, it's an example I like a lot about working memory. So one example, or a typical use case for working memory would be if I lost my keys. So my keys have disappeared, and we might go looking for these keys for the next 5 minutes or so. We won't do that, of course. But if you put yourself in the shoes of a person searching for the keys, it's actually pretty hard to tell what your working memory of that key, which enables this search, is. So is it something like a kind of photographic, pictorial, snapshot of what you've just seen? Probably not always. So at different times of the search, your key might also be a high-level concept, some abstractions of what keys are. And of course, in humans, you might quite quickly realize the whole baggage that comes with long-term memory. So when you're looking for your keys, you don't only memorize, it's only one item, right? But you don't only memorize this visual input, but you probably soon start thinking, where have I seen them last time? What doors do these keys lock? Etc., etc. Also, when you search different places, so when, for instance, you search in your purse or your regular purse, whether the keys are in there, you effortlessly transform this kind of visual cue into potentially somatosensory or auditory expectation working memory representation. And to me, this is so fascinating about working memory, that working memory is so flexible and adaptive to just transform the information just in the ways that we need it next. To put this on a bit more scientific or brain science grounds, one way of thinking about different formats of working memory information could be in terms of levels of abstraction. And this maps coarsely, it's not a new idea, it maps coarsely on quite established knowledge, so to say, about functional neuroanatomy, where we might think of concrete pictorial representations, or the other way around, we might think of early sensory areas as areas which have the machinery to present quite detailed sensory-like information, because they're also engaged in perceiving or sensing information. And as we move up the cortical hierarchy, which is to parietal cortex, we might assume representations to be more abstracted. So we know that parietal cortex, for instance, hosts representations of abstract magnitude or number or multi-sensory integration. And as you move even further anterior to the prefrontal cortices, there we know our representations of really abstract things like task, rules, goals, and also behaviorally relevant categorizations. And Radek is not here, unfortunately, but I think it's agreed that similar hierarchies also exist in object recognition along the more temporal areas. So levels of abstraction might be one way of qualifying format changes or different formats of working memory information, just as one idea. And just to add that we might also use different labels to describe quite similar continua or gradients. For instance, we might call them sensory to task-oriented, or in quite similar ways, retrospective, so what inputs have I received, to prospective, so what am I going to do with them. Just to finish this kind of introduction, one very important aspect in my view is to always keep in mind that working memory is probably not static. So that there is probably no such thing as just a freezing of information and rescuing it over time. But from all we know, and I won't consider all these important studies in detail, from all we know, there's tremendous moment-to-moment changes at all times, even during simple maintenance tasks. So that potentially we might want to think of working memory not so much of just storage in a memory sense, but much more in terms of computation, which is constantly in flux, so to say. So as I said, I want to present some recent forays from our lab towards these questions, and I want to begin with an eye tracking study. And this seems surprising perhaps, and also it has a longer backstory why we performed for the first time a purely eye tracking study in the lab. And Juan, who did most of the heavy lifting for this work, and we will probably have for the rest of our careers lots of anecdotes, which probably take a longer time. But just to accept, we started out with an eye tracking study, although it doesn't seem to be the most obvious thing to do if you're interested about information representations in the brain. I want to start with explaining the paradigm. So in the lab, we like to use such oriented objects as working memory stimuli. This has multiple reasons, in which I will come to in a couple of minutes. In this version of the paradigm, we first present two such oriented objects, and then retrospectively cue participants which of the two objects they have to report further object orientations they will have to report first after a delay period of various seconds. And only afterwards we cue them to report the orientation of the remaining object. So by and large, this is a typical dual retro cue paradigm, which is commonly used, where the assumption is that the currently cued information is in the focus of attention, whereas the currently uncued information, which has to be reported only afterwards, is deprioritized or unattended. Nodding to the idea that there might be two different states in working memory, in the focus of attention or unattended. So kind of a typical working memory task, just an extension to using naturalistic objects. But now to the eye tracking. Always makes me smile when telling about the eye tracking. So in this task, we used eye tracking to prevent that people move their eyes. So, and that was also the instruction, actually. That was not a lie. So we told participants, look, there is a high precision eye tracker directed at you, and it will make sure that we see that you keep your gaze still all the time at this tiny fixation dot. That was honest instructions, because Juan even implemented a closed loop feedback algorithm, which as soon as fixation drifted away by, I think, 1.5 or so degrees visual angle, there was a warning. Fixate. So one could summarize, we did everything in our power to prevent people from moving their eyes, which is also what we normally want to achieve in EEG and imaging studies. And I must always smile, but because in what follows, I will show lots of results about data which we told participants explicitly not to produce, in a sense. But let's first inspect the gaze distribution. So these are just overall aggregated heat maps plotted onto the, in scale, plotted onto the object sizes on screen. And it's not averaged, it's aggregated, like summed together over all trials, all participants. And we might conclude from here that people did more or less what we told them. So I'm not a year-long eye tracking expert, but to me it looks pretty much like people looked at the middle of the screen as we instructed them. However, if you look at it with some more magnification and average the eye coordinates separately for each of the object orientations that participants had to process in this task, we can discern pretty small such circular structures. So it looks like near fixation, there are tiny gaze patterns which seem to reflect the orientation of the cued stimulus that is currently on people's mind, so to say. And I want to give you some idea of the scale, of the spatial extent of these gaze patterns. So here's the attempt of an in-scale, roughly in-scale illustration here on the projector. So this would be an example object, this rotated tape recorder. And to get an idea of how large these stimuli were for the participant in their visual field, you can use your index finger. So if you hold your own index finger at arm's length, like this, then the size of your fingernail should roughly correspond to the size of this fingernail on the projector. So that was the extent of the stimuli. Now, importantly, it was a working memory experiment, so there was no stimulus actually on screen. So it was an empty screen, just a tiny fixation dot. And now to plot the gaze pattern that we identified in scale, we have to magnify this quite a bit on the screen. And now in scale, plotted in scale, on top of that, that would be coarsely. So it's probably not accurate to the millimeter, but approximately. That's kind of the extent of these gaze patterns. So roughly the size of a pinhead at arm's length, approximately. So now, of course, we want to do a quantitative analysis of these gaze patterns. And for this, we used RSA, representational similarity analysis, which also seems unusual for eye tracking data, but it's actually just stolen from neuroimaging. So we applied in pretty much the same way to this two-dimensional gaze space, X and Y, as you would normally in higher dimensional EEG or fMRI space. We use it here basically as a tool to filter the data in the first step, to filter the data for the presence of such circular structure. So that means we filter for this gaze pattern that we saw indicated just in the descriptive analysis. So we use it pretty much standard, just one small specialty. We do it on a single trial level. That has some advantages for us, but so we correlate vectors, not matrices, but the results are basically the same as if we would do standard, completely standard RSA. So doing this, and one nice aspect of eye tracking is that it has a good temporal precision, we can derive an encoding time course with millisecond precision of that orientation information that is reflected in the gaze data. And if we do that, we first see a pretty prominent encoding of the orientation of each of the two stimuli. And importantly, in the delay period, when there's no stimulus on screen any longer, we see a clear, sustained maintenance of these orientation-specific gaze patterns, which means there's kind of a memory reflected in these gaze patterns. We also observe something which, to my knowledge, so far has mostly been shown in single-cell recordings, namely that this activity increases, or activity, this encoding strength increases towards the end of the delay period, something which is often referred to as ramping up activity. And we see something similar when we look in the second delay period, but then, of course, for the other stimulus, which is now cued, and which has dropped slowly to baseline, then it was currently not relevant for the next step. So in all, we think this provides us with kind of a new tool, so to say, to track working memory dynamics over time. Now we wanted to use this to do some investigation into the format of working memory storage. And for this, it's important to note that in our paradigm, we use a set of different such objects. So it's not always the same object, but we have carefully selected according to certain criteria, as regards their shape, especially, differently shaped objects. Which means that we can test for the extent to which the gaze pattern, the orientation-dependent gaze pattern is associated with these objects, generalizes across different objects or not. To do this, we just extend our RSA model and ask about the encoding strength within objects. So to what extent the orientation information is represented if we, in pairwise comparison to the same object, just oriented differently, as compared to orientation encoding within, between objects now. So where we ask whether the pairwise comparison of different orientations between different objects also reflects such a circular structure. And the logic here is that by comparing the two, namely the strength of the within objects orientation encoding and the strength of the between objects orientation encoding, we get kind of a quantification of the extent of generalization across object. Simply, if the two are equally strong, we would assume that the orientation encoding is fully object independent. It doesn't matter which object was presented. People encode the orientation either way. And to the extent that the within objects encoding is stronger than the between objects orientation encoding, we would say this orientation pattern is object specific. It doesn't translate to another object perfectly. So if you look into this, just now plotting the same results I showed before again, but now separately for within and between objects orientation encoding, we first can see clear evidence for object-specific orientation encoding during the early encoding periods. So for the first kind of 1.5 seconds after onset of the stimuli, we see that the within objects orientation encoding is much stronger than the between objects orientation encoding. That holds for both stimuli upon presentation, but importantly, during sustained working memory processing, during all the delay periods, we see a change in that format, in the sense that now the between objects orientation encoding is equally strong, almost equally strong as the within objects orientation encoding, which suggests that the gaze patterns becomes ever more object independent. So it reflects the orientations, let's say, in a generalized, one could say, more abstract way. If you look at these patterns closely, we also see what looks like a systematic gradient of this generalization or abstraction, in that for the last presented item, we see actually some evidence for like residual object specificity being sustained throughout the first delay period. Whereas if you look at the first presented item, this does not seem to be the case as much. So the first presented item, which kind of is the processing of which is interrupted by the second presented item, seems to switch to a more generalized, or if you want, abstract format. And if you look closely, it looks also like this occurs rather rapidly. So you can see that the within objects information drops rapidly at exactly the point in time where the second presented stimulus starts to be processed. So this looks like could be indicative of adaptive format changes, which just adapt the working memory format to the current task requirement. At least as far as we can tell, like from the superficiality of eye movements. Just to add, and this is just repeating what I just showed, just plotted differently and presented differently in terms of base factors. So the proper way of quantifying these effects is presumably in terms of base factors, where we test for like equality of within and between and versus significant differences between the two. And this just recapitulates what I just said, that the format starts out upon presentation object-specific, we could say concrete, and switches to an object-independent format, which you might call generalized or abstract, and that we see actually the highest, so to say, degree of generality, actually for the second Q item. So the item which has temporarily been unattended and only afterwards is, so to say, refocused on. So that would be one potential shade of abstraction that we could assess with eye gaze patterns. One other shade of or one other expression of abstraction could be in terms of categorization of the stimuli. And here, in terms of categorization, we focus on a phenomenon which is well known in the orientation processing literature, a phenomenon called repulsion bias, which refers to the phenomenon that when people report orientations from working memory, their reports seem to be repulsed from the cardinal axis, where the cardinal axis are the vertical and the horizontal axis. So, like illustrated here, so that the responses concentrate along then the diagonals as if they were repulsed from the cardinal axis. And still not fully understood how these biases come about, but in our experiment with like real life objects, we might think of them as potentially higher level categorizations. So if you think of these oriented objects, that a participant, for instance, stores something like an abstract concept as points to the left or is turned upside down. So one could say a simplification which could contribute to such cardinal biases here, perhaps even in a non-visual, but rather more semantic, higher level way. So we asked two questions. One, do we see such cardinal biases also with our real-life objects? And second, do we perhaps even see it in gaze patterns? And we did observe clear evidence for cardinal repulsion bias in the behavioral data shown here. So we have all positive values. This is a model-based approach which I skip, but positive values indicate a positive cardinal repulsion bias. And we also see some indication of such bias in the gaze patterns. So the answer tentatively is yes. I say tentatively because the level of significance of this finding a gaze pattern is not on par with the very strong effects I showed you on the previous slide. So I think it may await some independent confirmation. But from what we tell, this could indicate that gaze patterns potentially even presage the occurrence of cardinal bias before they even manifest in the orbit button press response of the participant. And we likewise see here, similar as with the generalization results, we see that some indication that the cardinal repulsion bias, both in behavior and gaze, seems to increase after periods of inattention. So just like the generalization became ever stronger after inattention, a similar pattern seems indicated for the cardinal bias. And this also links, of course, to previous literature, at least in behavior, similar effects have already been shown before. So we kind of replicate or extend this here to real-life objects, which are oriented.
So how was the response given?
Sorry?
How was the response given for the orientation?
In this experiment, it was a left-right discrimination. So we showed a probe, it was quite similar, and people pressed left if it was clockwise or counterclockwise, like a two alternative.
It's like they didn't get how you quantify then the bias.
Yeah, you would, under the hypothesis of no bias, you would expect that errors are equal, like clockwise and counterclockwise errors are equally distributed around the circle. Whereas a repulsion bias predicts, and this is what's shown in this complicated plot here, a repulsion bias predicts that depending on which side of the cardinal you are, you have like a different asymmetry of these errors. So basically here we plot only the signed response errors that people show as proportions. So this can be assessed both with binary responses and with continuous reports. So to conclude this eye-tracking opera, one last thing we looked at, and this was actually suggested by reviewers who were interested in the oculomotoric causation of these effects, and therefore we added an analysis where we used microsecond detection and inspected the angles of these microcircuits as a function of the object orientation. And this analysis confirmed that the angle actually co-varies with the working memory information. So I don't think that proves that these effects are driven by microcircuits, but it is quite consistent with the idea that what these results show is really small, like some call it jerk-like, small, tiny eye movements, microsaccades at attempted fixation. So we don't know whether people are aware of it or do we intentionally, that's something we don't know, but it squares all pretty well with such a description that the oculomotorics behind that are tiny microsaccades. So to summarize this part, we find evidence for encoding of working memory information in eye movements. In tiny eye movements, in there we find some evidence for rapid and adaptive transformations, which we might refer to as abstractions or generalizations. And in there we also observe some evidence for gradual emergence of ever more categorical representations. So just because to attempt at least a little step into the future, also showing some ongoing work, so just briefly mentioning it. So yeah, very obviously for us, eye tracking became kind of a new kid on the block. So we are now quite heavily invested in running several eye tracking studies, and they're just focusing on just presenting the topics we focus on. One is multi-item storage. And we find preliminary evidence that these eye movements may even track up to 3 items. So even a working memory load of 3 and provide information about each of the 3 objects. So quite excited about that and what it delivers for addressing questions about multi-item storage. And so this is led by Felix Brühl. And in a PhD thesis or PhD work by Dilara Sorbeck, we also try to exploit these gaze patterns to track reformattings depending on task requirements. So these are quite intricate designs. I think you can already see that I don't have time for the details, but there too we have preliminary evidence that these eye gaze patterns are actually pretty sensitive in discriminating between different task settings, in this case, different contingency spaces. And of course, next time I will be very happy, or Dilara and Felix maybe will be happy to tell you more. But for the last, I think, around about 15 minutes, I wish to return to the brain and neuroscience and this idea of a gradient of abstraction in terms of a spatial gradient of abstraction in the brain. And in a sense, one might think maybe this is all too obvious. So one might even ask, well, what else would you find, right? So of course, concrete information is in early visual areas, and in prefrontal cortex you have for the abstract, like the complicated stuff. So we thought, but still, of course, we wanted to know, and put a version of the task that I just showed you to the scanner. And I should rather say Orisar put it to the scanner, so he's the mastermind and leader of all that work. But in a nutshell, we took our task and put it in the scanner. So now we might say, of course, but hold on. You just showed us that you have systematic eye movement patterns, and now you want to do neuroimaging. And of course, we were aware about this and had lots of sleepless nights about it. But fortunately, we found that there is a seemingly very simple measure by which you can almost get rid of these gaze patterns. And the simple measure is to not present the stimuli at fixation, but distribute them in space. So present them off fixation in the periphery. People can still do the task pretty well when you do this, which also I think has some implications for kind of the causality of these eye movements. So they don't seem to be necessary, if you want, for doing these tasks. But important for the neuroimaging, with that, and we have done lots of control analysis on that, we reduce these tiny gaze patterns by orders of magnitude. So many participants, they are then completely gone. So that we think it's good enough to do neuroimaging. In all other respects, the task was very similar as the one I presented during eye tracking. Just one small change in this task, we not only asked participants to report the orientation, but we also asked them to report the actual object they've seen, so they could toggle and find the correct object. So in our hope was, or the idea was that this encourages more concrete, more pictorial memorization, that potentially for this task, participants might want to really store the oriented object as such, and not some abstract parameterization of at 3 o'clock and it was a chair, something like this. So that was at least because we saw so strongly generalized abstract information in the gaze patterns, we thought, let's push the concrete side a bit. And of course, returning to that, we had a very clear expectation. We would probably see object-specific information, object-specific orientation representations in the early sensory areas, and maybe some generalization of the type we've seen in eye gaze patterns only further up from the parietal loop or so, where we would expect this. And in fact, we couldn't have been more wrong. So here's a RSA encoding time course of the object orientation for V1 to V3, but the same pattern is also can also be seen in V1. And we actually find both encoding time courses to be equally strong, which suggests a full generalization or abstraction of this orientation information, completely object independent in primary visual cortex, which honestly we did not expect, and probably would still today be looking for errors in the analysis if there hadn't been another paper, which I found a great paper, which was very impactful also for the directions in our lab, which showed something kind of similar. So, and I won't have time for all the technical details of this study, but Quick and Curtis found a generalized representation in primary visual cortex, which generalizes from grating orientation information. And grating is like the big workhorse in the literature, so people normally use oriented gratings. However, that representation seems to generalize to motion direction. So the direction of motion of randomly moving dots, which quite obviously is a completely different, like, sort of visual, and which tells a similar story, I think, like our finding, that orientation representations, even in the very early levels of visual processing, can be generalized and abstract. And one proposal by that study was that potentially what brain and capable people do is produce or use something like a surrogate stimulus, like just a line which indicates, so to say, the orientation, and which potentially can also mentally kind of visualize. It's also that we can't look inside the people. But similarly, kind of surprising finding, and we think that our finding speaks a similar language and perhaps conceptually extends it a bit by using these real-life objects, which per se have nothing in them which conveys the orientation visually. So the orientation information in our paradigm comes about only from world knowledge. So because people know that's like the real-world upright orientation of the stimulus, and accordingly, if I see it like this, it's turned left ways, upside down, for instance. In all other respects, we observe what many other studies observed before us, namely orientation encoding is strongest in the early sensory areas and in the early areas, and as we move up in the cortical hierarchy, it becomes a bit harder to read out this information, but still the information is reflected also in these areas. So we also find evidence for distributed representations of this information. Similarly as before, we also examined again cardinal repulsion biases, which we also find very strongly in behavior, also in this data set. And here the results pattern is similar, but slightly different. So here we use an approach just to explain. So we fit repulsion, or we use repulsion attraction models, which both are bad models, but the analysis situation is completely symmetrical. So we basically filter for extreme attraction versus extreme repulsion. And so by comparing the two, we get an estimate of the bias. So none of them is supposed to be a good model for the data, but when we observe the difference between repulsion and attraction, we interpret this as evidence for one or the other. And here we do not find any evidence for a bias in the primary visual areas, but we find increasingly stronger evidence for such bias if we move up the cortical hierarchy, and we find significantly then in parietal areas. And I saw in the timetable that Rosanne Rademacher's was here a couple of weeks ago, so you might already have seen a very similar result. So in what I think is a very nice paper, currently still a preprint, a very nice study with John Harris, I hope my pronunciation is not too off, and Rosanne Rademacher's, who report the same finding. So they also find evidence that further up in the cortical hierarchy, you see these kind of distortions or biases. So in this respect, we kind of replicate their finding. And I think together with the finding in terms of generalization, this seems to indicate that these two shades of abstraction do not necessarily occur completely in parallel. So they often accompany each other. So many factors seem to seem to promote both generalization and bias, but the two don't seem to be the perfectly same, perfectly linked things. There seems to be some degree of independence. So finally, as one extension to this investigation, we also were really cautious or careful in trying to address whether any of these results might have something to do with the specific stimuli that we used. So whether for some reason beyond our control, some features of the objects that we used might give rise to such generalization patterns, and that this extreme generalization is potentially just an artifact of the specific inputs we used for some reasons. So to look at this, we took off-the-shelf deep neural networks. Here it was just CoreNet-S as one classic, but the results are quite, we find very similar results regardless of which model we use. And this is work by Fabio Bauer, I should mention. I forgot to put a picture, I had one earlier. And here we just investigate, using the same analysis strategies, what happens if we apply these analyses to such off-the-shelf pre-trained model when we run our stimulus set through it. And doing this, we find, well, first of all, we find hardly any representation of this semantic orientation. These nets, which have always been trained to something completely different, they weren't trained on orientation, they just don't know really about the semantic orientation of these objects. But still investigating the layer activations, we find a representation of this orientation only in higher level areas. And this is not supposed to map somehow really on the brain, you know, that's not orientation models. But still, it shows quite clearly there is not even an orientation representation in these early layers of these networks, which makes it quite unlikely that something in the stimuli produces these results. And also we find that if anything, this whole orientation representation in the neural net is driven only within objects. So there's no generalization in this network. And the same holds for biases. So the model doesn't produce any bias. So that would mean that nothing of the results I showed you could be reproduced by just some hierarchical processing structure by itself. So everything what happens in working memory seems to come clearly from presumably top-down sources, and is completely different in a sense from what such simple perceptual model would produce. So lastly, we might ask, is there nothing concrete in the brain at all? Which seems counterintuitive, right? So if we think of the situation of the key which has disappeared, it's not that this picture is erased. At least that's how it feels. It doesn't feel erased or completely gone. And even subjectively, if you do these tasks, it doesn't feel like as soon as the stimuli have disappeared, there's a black wall and there's only an orientation parameter and some object ID number, so which you report. So that's not how we experience it, at least. And we can say that we do have some indications that there is indeed also some concrete information reflected, just much more in our fMRI analysis, but much more subtly. So one thing we looked at is the encoding of the spatial position of these objects, which we introduced as to control for artifacts. So which gives us, for I artifacts, which gives us access to, well, one more factor, just which we can decode, look at in the RSA analysis. And we do find evidence, also Q-dependent evidence, for quite well reassuring representation of this kind of episodic detail. So where on the screen has the stimulus been? And this is slightly remarkable perhaps because this feature is completely task irrelevant. So you will never, in the experiment, you will never be asked to report about the location. And so perhaps also having Felix here, I can say that we had many moons ago, we basically had the same finding in EEG, where we had a complicated sensory setup and also found that the EEG continues to reflect in a Q-dependent fashion the location of the stimuli, in this case left or right. And there we had the exact same situation, that the test required no report of this location ever. So it was completely task irrelevant, but still the brain seems to drag along some of this episodic, very concrete, I would say, trial-specific information during the delay. And of course, we have poor temporal resolution fMRI, but it looks like this declines, well, rather early, unlike the task-relevant information. And finally, this becomes a bit weird, but one other attempt to filter for the data for concrete information could be in terms of the silhouette of the stimuli. So I should have brought some object to rotate, but maybe it gets easier like this. So if we think of the orientation of these objects, and we didn't have such extreme long objects, but if we think of the orientation of these objects, it's quite evident that just the shape lives more in a 180-degree space than in a 360-degree space. So that these two orientations look very, very similar in low-level visual ways, but they are the complete opposite in semantic ways. So this is the opposite direction. And to examine potential representations of such lower-level shape-ish representations, we also looked at the encoding with the 180-degree model. And we find some evidence, it's not very strong, but we find some evidence, also again distributed, that this kind of shape information can also be read out from the multivariate fMRI data. So it's not completely lost what people have seen. And maybe this is another sanity check. If we now do the same thing with our, say, naive deep neural network, we can see this is information which the network can encode really well already in the early visual, in the early layers. And it's driven completely by within objects information, which is precisely what we would expect. So I think it's time for me to finish up. So to summarize, what have I written here? To summarize, we find evidence in the eye tracking for rapid and adaptive abstraction, mostly generalization of the task-relevant stimulus feature. We have this gradual emergence of categorical biases, gradual in terms of time and storage demands and working memory, but also gradual across the cortical hierarchy. So as these biases seem to, at least in our data, they seem to emerge mostly in higher level areas. And finally, the somewhat surprising finding potentially that such high level generalization or abstraction may also really recruit the earliest levels of visual processing in cortex. So perhaps few answers and many new open questions raised by this research. And but time to finish up. Thank you very much for the invitation. Thank you, of course, to everyone in the lab. And I'm looking forward to your questions.